So today we're going to take a look at section 5.6, which is indeterminate forms and L'Hopital's rule. That's how you say that, L'Hopital. He's a mathematician. People like to say Le Hospital. Yeah. There's no S in the middle, right? It's not hospital. It is L'Hopital. That's how we say his name. So L'Hopital's rule. All right, so the part that you may not like so much is we are going to think about limits again. But I think you're going to like the way we think about them, so just give it a fair shake. Wait before you decide. The basic idea when we evaluated limits was to get an expression changed into some form that allowed us to plug in the value for x. Do y'all remember that? So we did things like factoring, or we multiplied by conjugates to try and eliminate denominator. We were trying to eliminate problems that created a 0 over 0 when we plugged numbers in. But there are some forms that you can't do this for. These forms are called indeterminate. And they have the form 0 over 0 when you still can't, and factoring is one of the ways we deal with that. We're going to learn another way to deal with it. Infinity over infinity, positives or negatives, and then 0 times infinity. I actually had a professor in grad school who proved through the same algebraic manipulations that we all sort of intuitively think should work, that 0 equals 1. He proved it. Clearly, there's a problem with the logic, right? 0 does not equal 1. And as grad students, I remember we were all looking at it going, I don't see what you did wrong, but clearly there is something wrong with what you did, because it resulted in an answer that doesn't make any sense, right? And it was an indeterminate form situation. That's what it was. So we have introduction L'Hopital's rule. So if we have functions that are differentiable on a, b, and the interval a contains the number c, as long as g of x does not equal 0, except possibly at c. Okay, so it can't equal 0 the whole time. It has only at c potentially. Then if you have the limit of a rational function f of x over g of x, doesn't even need to be rational. It's in rational form, but it doesn't need to be rational. So f of x over g of x. Then the limit of that is the same as the limit if you take the derivative of the top and the derivative of the bottom separately. And that's not the quotient rule, right? That's what we wish the quotient rule were. It's not the quotient rule, but the limit is the same. The function value is not, but the limit is. Okay? This only works when f of x over g of x has an indeterminate form. So an indeterminate form means 0 over 0 or infinity over infinity, pluses or minuses aside. Now, I am not a super big fan of the structure of this statement. And the reason is this. They put the conditions at the end, right? It says all of this works if this part works. It's an if-then statement sort of in reverse. We usually see our definitions and theorems and so forth worded the other direction. So if you think about things like intermediate value theorem was one we did last semester, Raleigh's theorem, where they tell you if it's continuous and if the interval endpoints match, if these things happen, then this happens. That's what's going on here. They've just written it in reverse. Okay? So the first thing we have to do in order to make sure that we're going to be able to use L'Hopital's rules, we have to check the form. What will happen if you don't is eventually you're going to just be trucking right along and you're going to think you found the right answer, and it's not going to be the right answer because L'Hopital's rule didn't hold. And it didn't hold because the form was not an indeterminate form to start with. Okay? Yes, Sophia.
You're going to have to memorize this for the test.
No, I won't ask you to state it. No. Okay. You ready for an example? Okay, this is an example that we're going to do two different ways. We're going to do it first with L'Hopital's rule, the new way that we've learned. And then I'm going to show you how we did it in Calc 1 to verify that we ended up getting the same answer. Okay? So the first thing we're going to do is we're going to try and plug the number in, because that's what we always do, right? If it actually evaluates, then we would be done. So if I put the number -1 in for x, what do I get in the numerator? 0. And what do I get in the denominator? 0. That's indeterminate form, and I usually write an L next to it to sort of verify to myself that, yes, L'Hopital's rule applies. I really will be able to use it. Now, this is a very simple one in terms of taking the derivatives. Remember, as you're doing limits, you rewrite limit until you put the number in, okay? So that's why I'm still writing it. But what we're going to do when we apply L'Hopital's rules, we're going to take the derivative of the numerator. So what is the derivative of this numerator? 2x minus 2. And what is the derivative of the denominator? 1. All good so far? Okay. Can I put the number in now? Yeah, there's no problem now at all, right? In fact, the denominator is a constant, so there's no way it could be a problem now. So if I put the numbers in now, I would have 2 times negative 1 minus 2. And what do I get? Careful.
Oh, -4.
Negative 4. Yeah, negative 4. This limit's negative 4. And it really is that straightforward. Derivative of the top, derivative of the bottom, evaluate. Raise your hand if you like the rule. I'm a fan. I mean, let's be real. This is great. I want to show you, though, that it works the same way. This is an example that we could have done in Calc 1. In fact, I did an example very similar to this the other day in my Calc 1 class. And we would have done it with factoring. So I want to show you that if we factor, we get the same answer because we should, right? We should. If there's two ways to do something, we should get the same answer both ways. So if I do this from the standpoint of factoring, how will that numerator factor? X what? Minus 3 and plus 1. Does everybody agree? Okay. And what happens? Right? The x plus 1s cancel. And I can actually, whoa, good grief. Pen going crazy. I can actually plug the number in now, right? I have negative 1 minus 3. And I get negative 4. Okay. So that's great. It worked beautifully. And you might be thinking, well, but then why did we need a second way to do it? If I could have done it either way, what's the point? The point is they don't always factor and cancel out beautifully, do they? They don't. And sometimes even if they do, the factoring is really complicated. Like imagine it wasn't quadratic on top. It was cubic or it was quartic, right? You don't have a closed form for how to factor this. It could factor, but I mean, we're not going to factor something that's a power of 4 to start with if it had 5 terms. Like we're not going to do that. We have this other tool to be able to use. So take a look at this next one. This is a very good example of one where we don't have an algebra or a calculus 1 way to do this with algebra, right? This is not a factor cancel out situation. I do need to check always at the very beginning to make sure it's an indeterminate form. So if I put the number 1 in on the top, now the squared is on the x, right? Now, if you want to move the 2 down in front, you certainly can. That's fine. It's not going to hurt anything. We will later anyway before we take our derivative. So if you'd like to start, in fact, I'll just do it because we're going to do it anyway later. Start by rewriting the numerator with a property of log, you can. It worked just fine. Okay, so if I put the number 1 in on top, so this isn't calculus, right? That's an algebra or property. If I put the number 1 in for x, natural log of 1 is... Remember? 0. And I have 2 at the front, so this is 0 on top. What happens when I put in 1 on the bottom? I get 0 again. But factoring is not an option. But L'Hopital's rule works really nicely. So we're going to apply L'Hopital's rule, knowing that it does in fact work. And it's nice to have it written as 2 natural log of x, just because we avoid the chain rule process, right? So what's the derivative of 2 times the natural log of x?
2 over x.
2 over x. So you can either write it as 2 times 1 over x, or you can do exactly like Pierce said, and you can write it as 2 over x. That's the derivative of 2 natural log x. What's the derivative of x squared minus 1?
2x.
2x. Now, you're welcome to simplify that, right? Like, clean it up and make it look really pretty. But the reality is I'm just going to put the number 1 in for x anyway, and I can put it in here just as easy as I can put it in a cleaned up version, correct? So we can try it in here, and it will work just fine. 2 over 1 over 2 times 1. What will this give us? 2 over 2, or, whoops, just 1, right? Our limit's 1. Okay? Maybe just a couple more. Sine. We got our trig going on, right? All right. I realize there's an A and a B. They're just numbers that we don't know. Okay, so they're numbers. They're not variables. X is our variable. If I put 0 in for x, what is the sign of 0? Because A times 0 would be 0. What's the sign of 0? It's 0. And I actually have sign of 0 on bottom as well, right? So I've got 0 over 0. So it is in L'Hopital's, it is an indeterminate form, so I can use L'Hopital's rule. Okay, all good? All right, so we're going to take the derivatives. Okay, so what's the derivative of sine of ax?
Wouldn't it be a cosine ax?
Yeah, so cosine of ax is the derivative of the outside. The derivative of ax inside of sine is a. What we want to remember is that both of these are grouped together like this, right? It's a chain rule. So I have a cosine ax. What's the derivative of sine of bx? B cosine of bx, yeah. Now, it might look like we just traded sines for cosines. Did that help us? And the answer is yes, we did, and yes, it does. Right? We did trade sines for cosines. But it does help us because what happens when I put in 0 inside of a cosine? I get 1, right? I don't get 0 like I did for sine. I get 1, and that's just fine. So this piece, in fact, I'll write it out. So this is a cosine of 0 over b cosine of 0. Okay, the zeros are just canceling out the a and the b. They're multiplied by. And each of these is equal to 1. So I end up getting the ratio a over b. And a and b could have been anything we'd like. As long as b wasn't 0, I suppose, because then it doesn't make any sense, right? But anything else. Okay, is that good? Okay, every single one I've done so far, I've done 3, have had indeterminate form what? 0 over 0. So we really need to see one that does not have 0 over 0. That's our next one. If I put infinity in for x, remember infinity is not a number, but the concept of something getting infinitely large, right? So if I have a number that's getting infinitely large and I cube it, what do I have on top? It's infinity. And you may or may not remember all that we've done with e, but I do hope at least you remember the basic graph. It looks like this. So this is the graph of e to the x. It's not the graph of e to the x squared, but it's the same idea. And if you wanted to graph, the e to the x squared, you can see it in it, and it will look almost parabolic, like a parabola a little bit. The right-hand side's all I care about anyway. I care about what happens as my x values go to infinity, right? Because that's the limiting x values go to infinity that we're talking about. So as we go to infinity, think about what happens on the exponent here. This is not how you should say it, but I'm going to say it anyway. Infinity squared is infinity. And if you have e raised to an infinite power, you have infinity. Okay? So this is in infinity over infinity form. And therefore, we do have L'Hopital's rule that we can apply. All right, so what's the derivative of, Levi, yes?
I don't know if this matters or not, but is infinity over negative infinity 0 or negative 1?
Yeah, so it's actually indeterminate form as well. So it wouldn't be anything if you have infinity over negative infinity or the other way around. Like if there's a negative in there, it's still indeterminate. Yeah, yes?
So wouldn't it have like a plus or minus in front of that interaction right there?
For what part?
For infinity over infinity?
You don't need to denote positive infinity.
Do you mean like this, Adrian?
Plus or minus?
Well, it is positive here.
Oh, okay.
Okay, so it is a positive infinity. It doesn't actually matter. You're right, Piers, whether it is positive or it's negative. It won't change anything. But the fact that it's infinite and we are dividing infinite things by other infinite things means that the answer could result in anything. So depending on sort of how quickly things tend toward infinity will depend on what this answer is going to be. All right. In fact, as you see the answer, this is infinity over infinity, but if you flip it upside down, the answer would be the reciprocal of our answer we're going to have in a minute. We can get 0 out of this thing, we can get infinity out of this thing, or we could get any number possible out of this thing as well. And we don't know yet which one we're going to get. Okay? All right, let's give it a go. What's the derivative of x cubed? 3x squared. Cool. What's the derivative of e to the x squared? Good. E to the, oops, I didn't get that enough space. Let me see there. Hang on a second. E to the x squared and then times 2x. So, Sophia, where did times 2x come from? Right. It's a chain rule, right? Yeah. So we have to take the derivative of the exponent. The derivative of the exponent x squared would be the 2x. That's not written very well. Let me move it down just a little bit to make it clear. So the x squared is still the exponent. 2x is multiplied by the e. We can simplify this a little bit. This is a case where we would want to simplify this a little bit. Right now, if we simply attempt to put something infinite in, again, I'm still getting infinity over infinity. And we may still do so, but there's a reduction step that we can do to factor or simplify. In particular, one of these x's can cancel with one of those x's, right? So this actually simplifies a little bit to the limit as x goes to infinity. I have 3 on top. And I have, I'll move it to the front, 2e to the x squared on bottom.
Wouldn't it be 3x on top?
Yep, I lost one. Thank you. 3x on top. Okay, is that all right? What happens if I evaluate this as we go to infinity again? Okay, it's still infinity over infinity. What that means is that L'Hopital's rule still applies, and we do another step. Okay? This will be our last step, though. So in theory, depending on how high that power was, will depend on how many reiterations, how many times we have to do L'Hopital's rule. And you can do it multiple times in the same problem.
So that's why I hope to cancel.
Exactly. That's why it helped to cancel. If we hadn't canceled it, it would be okay. We could do it again, but not only would it not get there as quickly, but then we'd have a product rule in the denominator, which is not very friendly either. So cancellation along the way is going to be our friend, so that we don't have to do L'Hopital's rule more times than we need to or make it more complicated than it needs to be. Yep. Okay, so we're going to take derivatives again. So what's the derivative of 3x? 3. So I will not get infinity on top anymore, right? No matter what happens, infinity on top's not happening. Now what's the derivative of 2e to the x squared? E to the x squared times 2x. Again, you're welcome to try and simplify the denominator, clean it up just a little bit, whatever, but you don't really need to. The numerator, if I attempt to plug in infinity, is 3. We already talked about that. What happens in the denominator if infinity is what the x value is approaching? It's still infinity, right? So this doesn't always eliminate zeros and infinities, but what it does is it eliminates them from one location. It's not in both places. So now think about it. We did this in Calc 1. What happens if you take a number, 3, it's a constant, and you divide it by something that's getting infinitely large? It goes to 0. Right? Think about numbers. 3 divided by 1, 3 divided by 10, 3 divided by 100, 3 divided by 1,000. Remember tables we did in Calc 1? Right? As you divide it by something getting larger and larger and larger, the fraction gets smaller and smaller and smaller. This limit is 0. But imagine if the fraction had been flipped upside down and the e to the x squared is on top and the x cubed is on bottom, the reverse would have happened in this last step. Everything else would have been the same, just flipped, right? The reciprocal of everything. But in the bottom, we would have ended up, the last step, we would have ended up with infinity over 3. And infinity over 3 would be infinity as our answer. So that's why we can't just say, oh, if it's infinity over infinity, it's equal to 0. Or if it's infinity over infinity, it's equal to infinity. And depending, again, on the values, it could end up equaling a constant, and that would be acceptable as well. It just depends on the functions that we're using. I hope this section feels like a little bit of a breath of fresh air in the middle of all these derivatives that we're doing. They won't be as complicated in this section. We're not using product rules and chain rules, product rules and quotient rules for the most part. We're going to be using a little bit of simpler derivatives because we're not looking at the numerator and the denominator as an entire fraction, but we're looking at them separately. Any questions? Okay.